Good evening, everyone. My name is Basil Choma, and I'm here to discuss the distribution of velocity across a tube and its significance. Fluid flow, fluid flow through tubes is a fundamental phenomenon in fluid dynamics, governing processes in engineering, pharmacology, biology, and environmental systems. Now, what's a fluid flow? A fluid flow is the movement of fluids, whether liquid or gases, through confined geometries like tubes that are characterized by the distribution of velocities across the tube's cross sections. Now let's move to the importance of velocity distribution studies. The study of velocity distribution in tube is significant for both theoretical and applied sciences, both in engineering, pharmacology. Velocity profiles directly impact the design and efficiency of systems in engineering such as pipelines, heat exchangers, and chemical reactors. In pharmacology, it can be the preparation, formulation, and compounding of drugs or the drug delivery system. Let's move to the objectives of velocity distribution. The primary objectives of this seminar are elucidates the physics of velocity distribution, highlight practical application, explore measurement and modeling techniques, address challenges and future directions. Elucidates the physics of velocity distribution. It provides a clear understanding of how velocity profiles form in laminar and turbulent flows, including the underlying mathematical principle. That's Hagen-Poiseuille equation for laminar flow. That's an example. Then highlights practical application. It discusses how velocity distribution impacts in engineering design, pharmacology, industrial processing, and biological system with real-world examples. To explore measurement and modeling techniques, it introduced experimental and computational methods such as practical image velocimetry, that's PIV, and computational fluid dynamics, that's CFD, used to study the velocity distribution, address challenges and future directions, to identify current limitations in studying complex flows, example, non-Newtonian fluids, and propose areas for future research. Now let's come to the types of fluid flow. We have the laminar and the turbulent. Fluid flow in tubes is classified primarily into two regimes, laminar and turbulent, distinguished by the flow's behavior and the Reynolds number. So please, I need the marker. RE is the Reynolds number. A dimensionless parameter defined as, this is the formula, equals to RHO. Where RHO is the fluid density, V is average velocity, D is tube diameter, while MU is the dynamic viscosity. Laminar flow, typically occurring at RE less than 2000, is characterized by smooth orderly fluid motion with layer sliding past each other without significant mixing. The transition region is less predictable with flow characteristics depending on conditions like tube roughness or inlet disturbances. Let's move to the key parameters affecting velocity distribution. Velocity distribution in tubes is governed by several key parameters. We have the fluid properties, we have the tube geometry, we have the pressure gradient and the flow rate. The fluid properties, viscosity and density significantly influence flow behavior. Viscosity promotes laminar flow by damping disturbances, while low viscosity fluids are more prone to turbulence because I think I talked about the two types of velocity distribution. That's the laminar and the turbulence. So here it's saying viscosity promotes laminar flow by damping disturbances, while low viscosity fluids are more prone to turbulence. Let's come to tube geometry. The diameter and length of tube affects the regime and velocity profile. Smaller diameters increase shear stress, favoring laminar flow, while larger diameters may induce turbulence at high velocities. Pressure gradients. The driving force for flow, the pressure gradient along the turbulence determines the average velocity and shapes the velocity profile, particularly in laminar flow where it leads to a parabolic profile. Flow rate. The volumetric flow rate related to velocity influences whether the flow remains laminar or transitions to turbulence as higher flow rates increase the Reynolds number, that's this RE. Let's come to the role of tube geometry and fluid properties. Tube geometry and fluid properties play a pivotal role in shaping velocity distributions. Circular tubes, the most common geometry, produce symmetric velocity profiles with the maximum velocity at the center in a laminar flow fluid due to a no-slip condition at the walls. Non-cellular tubes such as rectangular and elliptical cross sections introduce complexities like secondary flows, altering velocity distributions. Understanding this interaction is essential for designing efficient fluid transport and predicting flow behavior in diverse applications. Now we have the velocity profiles in laminar flow. We have the parabolic velocity profile. We have the mathematical derivation of the parabolic velocity profile. This is it. U R equals to delta P for 2 minus R root 2. This is the formula. Where this is delta P is the pressure. Is the pressure drop over the tube length, and the mu is the dynamic velocity. The capital R is the tube radius. The small r is the radiant distance from the center line. Then we have velocity. The one we just discussed now is the parabolic velocity profile. This is the mathematical derivation. Then we have the velocity profiles in turbulent flow. We have flatter velocity profiles. In turbulent flow, the velocity profile is flatter compared to the parabolic profile of laminar flow. due to enhanced mixing caused by eddies and fluctuation. Let's come to the influence of Reynolds number. The Reynolds number is a critical parameter determining whether flow is laminar or turbulent and influences the shape of the velocity profile in turbulent flow. Factors influencing velocity distribution: tube diameter and surface roughness, fluid viscosity and density, pressure gradient and flow rate, boundary layer effect. Significance of velocity distribution in engineering application, pipeline design and optimization, heat transfer and mass transfer processes. Industrial relevance.
The time is up. Time is up.
Thank you.
Thank you very much. Please, let's clap for her. Please. What are you doing? Clap for her. All right. Okay, you're clapping for yourself with the back of your hand.
No.
Okay. All right. It's okay. I'm impressed, but I want to make one or two corrections.
Okay, sir.
Please, if you are working, please, this is for everybody here. Please, leave that thing you are doing. It's for everybody here. Please listen. I think I said this thing before now. If you are carrying out research, maybe you use AI or use any material. Once you copy a mathematical formula and paste in another document, a lot of things will change. It will tend to even trying to pronounce that thing the way you see rho. That rho you see there, that R is equal to rho. That RHO, that rho means is actually that symbol for what? Density.
Okay.
That P like this thing. So it will spell it for you. It will spell it for you rho.
Okay.
You know, you were like, when you were writing, you were like, I don't know the meaning of this, but that's what it is. It's talking about what? Density.
Yes.
The density of the fluid. Is that clear?
Yes.
Rho. I think you saw someone here wrote that thing on the board. Rho. Write it. Turn and write it. Write rho for the density on the board. Write it. Is it correct? Good. Now, another one, mu. You are not writing. You are not writing e. It's okay. It's okay. Please clean that e, please. It's okay. But you also the part I'm making now.
Yes, sir.
You see that? You see mu.
Yes, sir.
Mu.
Yes, sir.
That is not mu. It's mu. That mu for viscosity.
This.
Who are you looking at? Come and write on the board. Come. Shebi,
Come and
write on the board for us. You are there controlling her. Come and write it on the board. Oh, yeah, write on the board for us. That you are saying there, do it there. New. Let me see.
Okay.
The other tail should come up a bit. The tail should come up a bit.
Tail.
End should come up. Take it up a bit. No, I mean like this now. Form U shape around that ending. Small U shape around that ending. That's the other end again. She also form U shape around that. So like that. Is that clear?
Yes, sir.
So that's what they are pronouncing for you as what? Mu. So that's the meaning of MU. Now come over to that end. You see that MU? You see it again.
Yes, sir.
Please, that thing you see there, that thing like this. Watch. This like that is over.
Okay.
That thing is over.
Okay.
After this, now go back to the formula you copied. You find out that how the formula is. Okay. You see that R. You see R squared. R. That thing means R squared. That like look like a bridge.
Okay.
Is R squared. So clean it. It's R squared minus capital R squared minus exactly like that's the meaning. It's because you copied it and pasted. So they change a lot of things. So next time you're copying, please look at it again and correct it so that it doesn't reflect on your work.
Yes, sir.
All right, so that's the correction I want to make there. All right, thank you very much.
Thank you, sir.
Thank you very much. God bless you.
Was remaining.